Now let's look at this particular situation. We have a normal population. We know the standard deviation of this normal population. We do not know his mean. That's why we try to estimate the mean of the population. Okay. So we know the standard deviation of the population. This is the distribution of the normal population. Okay. This is the mean. We do not know the value of this mean. Okay. Now, from this population, we take a sample. The sample size is 24. Then we obtained a sample mean 27. Okay, from a normal population, we take a sample size 24, and we calculate the sample mean, which is 27. Now, think about this moment. Okay, think about this question for a moment. If from this normal population we take all possible samples of size 24 and calculate sample means every time, we would obtain all possible sample means of size 24, right? And all these sample means of size 24 would form a theoretical sampling distribution of the sample mean, such as this one. Okay. Now, this theoretical sampling distribution of the sample mean should also be normal. Also, for this theoretical sampling distribution of the sample mean, the means of the theoretical sampling distribution of the sample mean should be equal to the population mean. Although we do not know its value, we do not know the value of the population, therefore we do not know the value of the means of the theoretical sampling distribution of the sample mean, but we know that these two values, these two means, should be identical. Okay. All these are from the central limit theorem. Make sense? Okay. So, let's come back to the question. Now we take only one sample of size 24 and we obtain the sample mean 27. Now, this sample mean 27 actually is a number, is a value within this theoretical sampling distribution of the sample mean formed by all sample means of size 24. Make sense? That is, this sample mean 27 is actually just one value in this theoretical sampling distribution of the sample mean that is formed by all sample means of size 24. That is from the central limit theorem. Also remember the fact that the theoretical sampling distribution of the sample mean is a normal distribution. Okay, now look at what we have here. We have a normal distribution, and one value of this normal distribution is 27. That's sample mean. Now, this is one value in a normal distribution. That tells us that this particular value, 27, has 68.26% probability comes from an interval 1 standard error around the mean. So this sample mean 27 has a 68.26% probability comes from an interval which is one standard error around the mean, because we are talking about this is the normal distribution. For individual value, it has 68.26% probability to be located within an interval one standard error on both sides of the mean. See, this is the area bound by one standard error below the mean, one standard error above the mean. This is a lower bound and upper bound. The lower bound is one standard error below the mean. The upper bound is one standard error above the mean. Within this bound, you have 68.26% of all sum of means. In other words, any individual value within this distribution has 68.26% probability bound by this interval, one standard error below and above the mean. Of course, any value in this distribution also has approximately 32% probability not bound by this interval, but fall outside the interval. But now we are talking about the 68.26% probability for value fall within this interval. Let's say that I'm 27 has 68.26% probability fall within this interval. Let's say this is a particular sum of mean, 27, right there is fall within this interval, which has 68.26% chance. If that's the case, let's look at this. Here is the mean of the distribution. Here is the sum of mean 27. Okay. And this is the upper bound. Okay. Now look at this. The difference between the mean and the sum of mean 27 is this. From the middle to this point, the difference between the mean and the bound is from this point to the upper bound here. Okay. Now, from the mean to the upper bound is the half of the entire interval. Half of the interval is one standard error, right? Half the interval is one standard error. Since we said that this interval is one standard error below the mean, one standard error above the mean, the whole width of the interval is two standard error. Therefore, the half of the interval is one standard error. From the middle point to the upper bound is one standard error. If this sum of mean 27 has 68.26% probability fall within this interval, so you can imagine the difference between the mean and the sum of mean 27 cannot be larger than one standard error. The one standard error is from the mean toward the upper bound. One standard error is from the mean to the upper bound. The difference between the mean and the sum of mean 27 is from the mean to this point. So the difference between the mean and the sum of mean 27 cannot go beyond this one standard error. Make sense? And this happened 68.26% of the time. So this is very crucial. So if you understand this, everything else becomes easy to understand. Okay, so 68.26% of the time, the difference between the mean and the sum of mean 27 cannot go beyond from the mean to the upper bound. Is obvious. This idea is expressed as this equation, as this. So this is the mean, the difference between the mean and the sum of mean 27. This difference cannot be larger than 1 standard error. Now we express the difference between the mean and the sum of mean 27 using this absolute sign. Okay. Using the absolute sign means that actual length. Okay. So this inequality is very important. So if you understand this, everything else become easy. So this is the crucial point. You have 68.26% chance that this is true for a normal probability distribution. Okay? Okay. And after this, we open up this absolute sign. We obtain these two expressions depending upon the positive, negative situation. These are from school algebra. We do not go into details here. And from this, it can be written as this. You just switch side for different terms, and to change from this to this. Then from this, you can change it to this again for terms. You switch sides. These two different expressions can be written as one inequality, as this. Now, this is the expression that says that the means of the theoretical sampling distribution of the sum of mean is bound between a lower bound and upper bound. The lower bound is mean minus 1 standard error. The upper bound is mean plus 1 standard error. But we know from the central limit theorem, the means of the theoretical sampling distribution of the sum of mean is also equal to the population mean. Our main focus, our interest here is the population mean, since we want to estimate the population mean. So we can rewrite this inequality as this. We can substitute the population mean for the mean of theoretical sampling distribution of the sum of mean. We write this. We call this inequality as a 68.26% confidence interval. In other words, we are 68.26% confident that this interval encloses the true population mean. So this interval has 68.26% probability of enclosing the true population mean. Now we just set up this interval. This is a 2 point. One point is the lower bound, another point is upper bound. We use this interval to enclose the population mean with this level of confidence. We are 68.26% sure that this interval encloses the true population mean. Now we can plug in the actual value that we know to calculate the value of lower bound and upper bound. The question already gave us that the mean, the sum of mean is 27, so we know this value. And this value is standard error, which can be calculated from the population standard deviation and the square root sample size. Population standard deviation, we know, is 6.5. The sample size is 24. So we can actually calculate the lower bound and upper bound. 27 minus the standard error. 27 plus standard error. And we complete these calculations, we obtain the lower bound and the upper bound. And this lower bound and upper bound created this interval we call 68.26% confidence interval. So we are 68.26% sure that this interval includes the population mean. Now you may say, that about 68% is not quite high. Can you be more precise? Can you be more? Can you have a interval over which we are more confident that the interval enclose population mean? Yeah, we can do that. Let's say we are 95.44% confident. Since this is a normal distribution and the sum of means 27 would have 95.4% probability comes from a interval 2 standard error around the mean. 2 standard error below the mean and 2 standard error above the mean. Or within this interval, you are 95.4. You have this within this interval. There are 95.44% of all sum of means, and this particular sum of mean 27 has a 95.44% probability among them. And if that's the case, again, the difference between the mean and this sum of mean cannot be larger than the difference between the mean and the upper bound. And this happens 95.44% of chance. So that is the difference between the mean and that sum of mean 27 cannot be larger than 2 standard error. And if that's the case, we open up this absolute sign, we obtain two expressions, again, positive, negative, and they can be rewritten as this, two separate expressions, and the two separate expressions can be written as one inequality, and then we substitute the population mean for the means of the theoretical sampling distribution of the sum of mean here to obtain this expression. This expression gives us a 95.44% confidence interval. We're 95.44% sure that this interval encloses the population mean. Then we can bring in the actual value of the mean and standard error to obtain the actual lower bound and upper bound of a 95.44% confidence interval. So now with this new interval, we are 95.44% sure that it encloses the true population mean. Similarly, if you want to be more confident, we know you can build a 99% confidence interval and with the 3 standard error. So we do not go into the graph anymore. We can directly write that if you want to be 99% confident, you just build a larger interval and with 3 standard error on the both sides of the mean, and therefore the difference between the mean and the sum of mean 27 cannot be larger than 3 standard error. And you open up the absolute sign and you obtain the series, these two expressions going through the same process. Eventually you come up with this expression with the lower bound and upper bound. We call this 99.74% confidence interval. Then you bring in the actual value, you obtain the lower bound and upper bound of 99.74% confidence interval. Okay, now let's summarize what we have done. What we have done here is find the lower bound and upper bound of a confidence interval. For the 68.26% confidence interval, what we did is to find that the population mean is enclosed within this lower bound and upper bound. This lower bound is mean plus 1 times standard error. The upper bound is mean plus one times standard error. So lower bound is mean 1 minus 1 times standard error, and upper bound is the mean plus 1 standard error. And for 95.44% confidence interval, we have this expression. The lower bound is mean minus 2 standard error, and upper bound is mean plus 2 standard error. For 99.74% confidence interval, the lower bound is mean minus 3 standard error, and upper bound is mean plus 3 standard error. Did you begin to see some pattern here? With different level of confidence, you have a different value here. You have different value here. What is this 1, 2, 3? 1, 2, 3 are the z-scores that correspond to a particular level of confidence. We know that for 1 standard error below and above the mean, you have 68.26% sample means. And within 2 standard error below above the mean, you have 95.44% of all sample means. So this 1, 2, and 3s are the z-scores that correspond to 68.26%, 95.44%, and 99.74%. And they are all integers. I use those integers as a convenient way to introduce the techniques of interval estimation. But many times you do not need those different 3 strange value of confidence. And seldom you hear people say that I want to have an interval for which I'm 95.44% confident that the interval includes the true population means. More often people say, let me have a 90% confidence interval, let me have a 95% confidence interval, let me have a 99% confidence interval. They do not say that let me have a 99.74% confidence interval. So for any level of confidence, outside those level of confidence that would give you the integer z-score, for any level of confidence, we have a general expression. The general expression for any level of confidence is very similar to these 3 expressions, except that we change to a general z-score, not just a z-score of integers 1, 2, 3. We change, we use z-score that correspond to a general level of confidence, any percentages, not just these 3 percentage that would give you the whole numbers of z-score. This z-score correspond to any level of confidence, any probabilities. Okay, so this is the general expression of the lower bound and upper bound of a confidence interval. Now, if you look closely at the expression of the lower bound and upper bound, they can be succinctly expressed as this. You know, the lower bound and upper bound of a confidence interval can be expressed as mean plus minus z-score times standard error. Okay, this when you use the mean minus z times standard error, that gives a lower bound. When you use the mean plus z-score times standard error, that gives the upper bound of the confidence interval. We use this, I like to emphasize, we use this way to calculate lower bound and upper bound of a confidence interval when we know the population standard deviation and the sample size could be any small size or large size, regardless, as long as we know the population standard deviation. Why is that? Because to calculate the standard error, we need the population standard deviation. Okay. One more thing before we look at one example here. How do we express a confidence interval? After you obtain the result, how do you express a confidence interval? Three ways to express a confidence interval. First, you put the lower bound and upper bound in the parentheses. The smaller number to the left, the upper bound, larger number to the right. We always put the smaller value to the left, larger value to the right, separated by a comma. Second way to express a confidence interval is use this expression. Okay. The population mean is enclosed between these two values. This inequality. And the third way to express a confidence interval is to draw a number line and mark the lower bound and upper bound, and also write down the actual value. In your assignment, you can use any one of the three. You do not have to use all three. Use any one of the three will be okay.